Hi, I'm Hang.
And I'm Sybil.
We are conducting an organic chemistry research under Dr. Gian. Our primary focus is to create biologically active molecule that can incorporate silicon selectively into specific positions within an aniline-contained drug compound. Aniline is an organic compound that consists of a benzene ring and an amino group, and it is important in drug making due to the stabilization effect. Carbon and silicon are isosteres. Silicon can increase metabolic activity and the permeability of the molecule into cell membranes, and this is why it's a good replacement for carbon. For example, imatinib can be used to treat tumors. It works by blocking the action of abnormal protein that signals cell to replicate, which stops the spread of cancer cells. If we could add a silicon cyclic group to the ortho position that is next to the aniline, we can then hypothetically increase drug delivery. Drug delivery basically implies the amount of time it takes for the drug to start working. Efficient drug delivery can improve patient well-being and economic efficiency.
The three known methods to add a molecular group to a benzene ring in a certain position is aromatic electrophilic substitution, where we get a mixture of products and our desired ortho product is reached only at 2%. The other known method is directed metallylation using a strong base. Using a strong base isn't favorable since the strong base will react with other hydrogen molecules and create other compounds that we don't want. We can also use a pre-functionalized substrate where we already have a bromine on a benzene ring, and then we just replace that and get our silicon group added there. But to synthesize this first substrate, we have to go through a lot of subsequent reactions, which create a mixture of products, final products. The main point of our research is to create a 9-NO-silylacetal molecule, which is a molecule with nitrogen, oxygen, and a carbon atom. The problem with this molecule is that it is very unstable and it goes through several types of reduction. The first type of reduction is a reductive nitromanic cyclization, where an NO2 group is added instead of the silicon or reduced to the NO2 group. We can also have reductive nucleophilic addition, where a nucleophile or an electron-rich molecule will attack the silicon and replace it. We can also have exhaustive reduction, which is what we encountered during our research when we try to have two N-O-silylacetal groups added onto these two positions on a benzene ring. We were only able to get the N-O-silylacetal at this position, and this position here went through exhaustive reduction. So to get our expected product, we had to go through further research.
For our hypothesis, we need to make nitrogen electron deficient in order to stop the exhaustive reduction, and this can be done by putting an electron withdrawing group on the nitrogen. We have experimented with the Bach and tosyl chloride group, and we're still working on this third one. The CH bond is being activated by the addition of silicon. This can stabilize the N-O-silylacetal. An example of using Bach as the electron withdrawing group. This reaction could produce a mixture of products where the middle product is what we want. We started the experiment by installing the Bach and tosyl chloride on the nitrogen. The yields came out to be fairly good compared to the reported yield, as we have only done this once. For this reaction, we have only reduced the nitro group, and we are still working on installing the trifluoromethoxide onto the nitrogen. For preliminary research, here we have successfully isolated our desired NO-silylacetal intermediate. By treating this with iridium and ligand, we will be able to achieve our desired product, which we are still working on. The future plans show the different reactions we can do with this molecule to produce these derivatives that can be helpful to modify the already existing compounds introduced in the background slide.
Our starting materials have been synthesized using acetylation and Bach protection from aniline, and iridium catalyzed hydrosylation was performed over model substrates to prepare stable NO-silylacetal intermediate, which is something that no other research lab has been able to do before. Our research is sponsored by NIH and NSF. Thank you so much.